Hello everyone, so welcome to some notes about projectile motion. Here's a couple of examples of projectile motion. So if this guy fires an arrow and it flies through the air, that's an example of projectile motion. Or maybe we throw something off a cliff, right? So we throw this off a cliff, it falls to the ground. That's an example of projectile motion as well. One of the things to note about these is that they have things going on in both the x and the y direction. So this is a good example of two-dimensional motion, right? We have things happening in the x, we have things happening in the y. That's two dimensions. So what is a projectile? So a projectile is any object which projected by some means and continues to move due to its own inertia or due to its own mass. Right? So once you let go of it, it's flying through the air. There's nothing else acting on it. Right? There's no rocket attached to it. There's no parachute on it. Whatever it is, it's just flying through the air on its own. The trajectory is going to be the path the projectile takes. So for projectile motion, assuming no air resistance, that path is going to be a parabola. Right, so I have this nice parabolic shape to the trajectory. Now, projectiles do move in two dimensions, right? So this is just a diagram that shows the x and the y components of the velocity, right? So if you pick this point right here, this object has some motion in the x direction. It's moving that way, but at the same time, it's still going up. So it also has some motion that way. So it has velocity or speed in the x and in the y. So we're going to call those the horizontal and the vertical components of these vectors, of the velocity vector in this case. So what about the horizontal velocity vector? Well, that's never going to change. If you think about it, right, once you let something go, gravity's pulling it down, so there's an acceleration downward. That's going to change the vertical velocity. But the acceleration downward doesn't do anything to the velocity this way, right? So your horizontal velocity winds up staying constant. Okay, so if I look at this diagram again, these blue arrows represent the x component of the velocity, and they're the same length all the way through, right? So they don't change. So what does that mean? Well, let's say it's moving at 1 meter per second. After 1 second, it's gone 1 meter in the x direction. After another second, it's gone another meter in the x direction. And that's just going to continue on and on and on. But what about the vertical velocity component? Well, the vertical velocity component does change. Okay, it does change, right? So here are my red arrows, right? I start off with a velocity upward. That's why the object moves up some. I still have velocity upward, but now the magnitude is a little bit less. The arrow is a little bit shorter. When I get to the very peak, I have zero velocity in the y direction, right? This is the same thing if we throw a ball straight up and then it comes straight back down. At the very peak, the velocity in the y direction is zero. Then the velocity changes directions. Now it's coming back down. So I have a downward velocity, and as it goes down, it gets faster and faster and faster. So the y component of velocity increases in magnitude on the way back down. And it's not going to cover equal displacements and equal times. Unlike before, where equal displacements and equal times meant a constant speed, now it's going to cover different displacements during equal time intervals. So with the vertical velocity component, both the magnitude and the direction change, right? On the way up, the velocity is positive. On the way down, the velocity is negative. The same way if you do something up and down. As the projectile moves up, the magnitude decreases and its direction is upward. As it moves down, the magnitude increases and the direction is downward. Okay, so let's look at horizontally launched projectiles. So if I'm going to take some, I'm going to call this dog my projectile, right? This is my object that's going to fly off the edge here, fly through the air, then land over here in the water. This is actually a diagram that comes from, I don't know if you've ever seen they have these dog jumping competitions where they basically throw a toy off of the end of a dock and they see how far the dog can jump into the water. So I've got this dog, he's running, he's going to jump off the end over here, and how far does he go, right? So if it's being launched horizontally, right, he's flying off with a initial velocity that's horizontal. I start off with no initial y component to the velocity, right? All my initial velocity is in the x direction. There's no velocity in the y to start with, right? We know that's going to change because after he flies off, his y velocity is going to be down and that magnitude is going to get greater, right? If I come back to this diagram here, it's really the second half of this, right? So we're starting here and the dog's going to fly off that way. So the initial velocity in the y direction is 0 for horizontally launched projectiles. Now, the initial velocity in the y is the same as, the initial velocity in the x direction is the same as the velocity in the x direction anywhere the dog is jumping, right? Anywhere in the air here, the x doesn't change, so that's going to be constant. What about projectiles launched at an angle? Well, if I'm launching the projectile at an angle, so here I've got a basketball and we're just going to kind of throw that up in the air, it's going to land way over here. So the initial velocity is at this angle theta, and I have some x component to that velocity, and I have some y component to that velocity. Well, how do I know what those components are? Well, the x component is going to be the initial velocity times cosine theta. Because if you look at this triangle here, right, this is the adjacent side. So the adjacent side is going to be the hypotenuse times cosine theta. And what about the y component? Well, the y component is going to be the initial velocity times sine of theta. So this component here, this is the opposite side of the triangle, right? This cosine and sine for the x and the y component will always be true as long as you measure theta from the horizontal. Okay, as long as I measure theta from this horizontal line over here, then the x component will always be vi cosine theta. The y component of the initial velocity will always be vi sine theta. So there you go, right? So the initial velocity in the x, v naught cosine theta, the initial velocity in the y, v naught sine theta. So vertical and horizontal components are independent of each other, and therefore equations of motion can be written for each direction, but they must be kept separately. So you've seen these are kinematic equations again, right? And they apply in the horizontal direction and they apply in the vertical direction, but everything has to be kept separate. This is the x displacement. This is how far horizontally it goes. This is the y displacement. This is how far vertically it goes. Now, because there's no acceleration in the x direction, this all goes away. Right? This whole term right here is 0 because the acceleration in the x is always 0. In the vertical direction, the acceleration is always due to gravity. That's your negative 9.8. That's your value for g. Okay? And these v naughts here, right? V naught y and v naught x, those are the same thing from the slide before. Those are these, v naught cosine theta, v naught sine theta. So there's a couple things that we need to consider when we're doing these type of problems, right? So first things are separate your components. Right? Identify what the initial velocity in the x is. Identify what the initial velocity in the y is. Identify what the acceleration in the x is, which is 0. Identify what the acceleration in the y is, which is negative 9.8. And then put those into two columns. Separate them, right? They don't cross over. Vector quantities need to be kept separate for those two directions. If it begins and ends at ground level, so like this example here, right? If the ball starts here and then ends over here and stops there, the y displacement is 0. Right, if I start from ground level and I end at ground level, up and down, the total displacement in the y direction is 0. You need to remember that the y velocity at the peak of the trajectory is 0, right? My y velocity up here is 0. My x velocity is not. My x velocity is the same as it was the entire trip, but the y velocity is 0 at the peak. The x velocity is constant everywhere because there's no x acceleration, right? This component here is the same as that component there, which is the same as that component there, there, and there. The x velocities don't change. And the time up is equal to the time down. Now this is one that maybe not be totally intuitive, right? But think about this. This is a symmetric parabola, right? So if it takes 2 seconds to reach the peak, it's going to take 2 seconds to reach the other end as well, right? And the total time in the air would be 4 seconds. Okay, I'll work out a couple of these example problems in class and probably post a video going over these example problems as well. Thanks.